molecular singularities in AdS CFT. Okay, so first of all, maybe some useful references that you might find useful. These are the papers that originally discovered and described the black hole singularity in the context of gravitational holography. So there are two original most important papers. One is from 2003 by Schenker, Benny, Levan, and Fikowski. And then very soon afterwards, this is a paper from 2005 that actually makes things much more clear by Liu and Festuccia. And then one also maybe just quickly mention one other paper that developed some OPE techniques that we are using in all the papers I wrote or we wrote. And now the paper that this is talking based on is the recently published paper, which basically gives new perspectives into the black hole singularities in AdS. Okay, so this is just the necessary part of the flow. Now let me just quickly mention the outline and then we'll start. So I will try to first give you some setup and introduction to what AdS is and what we will be doing. Then I will tell you something about the structure of geodesics. And then at the end, I will try to give a new point of view using some recently developed understanding of the OPE structure of the CFT side of the story. Okay, so if you have any questions at any time, you can always ask. That's I think that's more useful than we'll really go through everything. So the first part, so the setup. So let me just give you some very quick introduction to AdS CFT. I think in all those to AdS CFT, this is a necessary part. So what is AdS CFT? So it is a duality, a weak strong duality between the quantum gravity in the aspect of the AdS spacetime in d plus 1 dimension, and this theory is dual to a CFT on its boundary, which is codimensional 1, which is d dimensions. Now, what is meant by this is that the partition functions are the same. So if you take some quantum gravity theory in asymptotic AdS spacetime, such that you want your fields in the theory to approach some boundary value phi hat. So this will be the same as the path integral or the partition function for the CFT, which is sourced by this phi hat. Okay, so this is is basically a statement between of equivalence between these two theories. So you might there are many philosophical ways how to understand AdS CFT. So in a way you might ask like, okay, I know that the asymptotic symmetries of AdS spacetime are basically the same as the conformal group. So from a symmetry point of view, you naturally expect to have some kind of CFT on the boundary. And moreover, once you assume a dynamical gravity in the bulk, this is automatically mapped into a stress tensor in the CFT. So basically, you can axiomatically, in a way, almost axiomatically build some CFT starting with basically any quantum gravity in the bulk. So this is not a very non-trivial statement. This is just from symmetry reasons, starting with any quantum gravity, you will get some CFT. So from this point of view, there is no non-trivial information. But what's the point in this is that generally you get ugly theories both sides. So starting with any quantum gravity in the bulk, you will usually get some CFT which will be ill-defined, which means it will be non-unitary, it will be non-local. So the question really is, so what are the nice examples of this, where both sides have some physical and relevant meaning? So there are two approaches to AdS CFT, two main flows of research. One is called the top-down approach. So top-down approach treats AdS CFT as more or less a string theory concept, where they study concrete examples, and, in, 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 where we know both sides, and we know that both sides are well-defined and are physically relevant. This includes the study of the famous for superunions being dual to be supergravity in AdS 5 process 5. So you can either study concrete examples. Many people actually treat AdS CFT as just a study of this particular example or just several handful of other examples, where we basically know both sides and we are interested in both sides, and they treat it like this. But what we do, for example, is a more recent approach, bottom-up approach, where the question is posed differently. So our question is, so what's the minimal set of conditions? So we are searching for minimal set conditions or constraints for both sides to be nice in a way. Which of course includes we want it to be causal, local, we want it to be unitary and easy to work with.
So the constraints are implemented where?
So the constraints, very good question. So we treat it from a CFT side first. So what we introduce is the concept of holographic CFTs. So holographic CFTs. So holographic CFT is a CFT which is believed to have a well-defined and nicely behaved gravitational dual. And this is given by two conditions. First of all, we require large central charge in the CFT. Central charge, so we will generally work with CFTs in higher dimensions. So here you also have central charge as you would have in 2 dimensions, but the situation is a bit more complicated. But still, central charge is defined as the coefficient in the stress tensor 2-point function. We want it to be really huge, which means we are considering systems on the CFT side which has many degrees of freedom. The second condition is that we want a large gap. It's called large delta gap, which basically means that we want all the operators that in the CFT whose spin is higher than 2 has to have very large scaling dimension. So scaling dimension is the quantum number for the CFTs. So these are basically 2 CFT conditions. And currently, this is believed to be the minimal set of conditions up to some very small subtleties. This is the minimal set of conditions that, thanks to these ones, first of all, having large CFT on the boundary, this is dual to having semi-classical limits, semi-classical gravitational dual, semi-classical gravity, while having large gap. This is basically, for people that are familiar with NX4, this means that you want a large M in your theory. And now the large gap basically ensures that there will be no higher derivative corrections in your gravitational Lagrangian. So this basically means that you will only get Einstein-Hilbert actions, we will get a classical general relativity. And thanks to these 2 conditions, it is believed that you will automatically get a unitarity on both sides, automatically get all the properties that you want.
So it means that they are sufficient, but they are not necessary. Like in the minimal can mean different things.
Yeah, exactly.
So you know, in pure totals, you are more or less ensured that.
Yes, but there exists even lower set of constraints.
And you want to have somehow find weaker constraints. That
yes,
still
in ideal case, we want to somehow have the minimal possible bootstrapping of what CFTs give a nice holographic duals. I mean, you might also eliminate this first or even the second constraint, and then you will have some gravities. For example, string corrections. You will have some higher derivative corrections in your gravity, and that will have also some quantum corrections. But in these cases, you will generally get non-unitary theories. So it's in the current view of this bottom-up holography, we basically strictly restrict ourselves into large CFT and large gap. And this ensures that everything will be very fast. And this way you can study broader class of theories than just some concrete examples like n equals 4.
Well, what's the difference between delta gap and delta J bigger than 2?
So delta gap basically means that the delta gap is the scaling dimension of the lowest lying higher spin operator in your spectrum.
So J is bigger than 2.
Exactly.
So it was the same.
Sorry, it was the same, okay, so and this is what we do. So concretely, the most studied model in this setup of holographic CFTs is CFT, which is dual to the minimally coupled scalar in the graph. So it is the model that is dual to this type of theory. So we will have r squared minus m squared phi squared and plus the Einstein projection. Okay, this is the most studied model. Okay, actually, on average. So you basically have a free massive scalar field in the Valach, which is minimally coupled to the gravity, and you have just the Einstein gravity, so there are no higher relative interactions there. Okay, so this is a nice model because well, it's basically the simplest one that you can imagine. I mean, you can also imagine a theory where you only have Einstein number of action and you study perturbations of the metric. That's what we were doing in the last project, and that's also very interesting because this way you can study stress tensor correlators on the boundary, and it can give you some nice physics. But anyway, so this will be a theory that we will be working with. Okay. Now. Okay. Now, how to use AdS CFT? Because it's nice that we have some kind of duality, but how to work with it in practice? So thanks to the fact that we have a semi-classical gravity, we have a semi-classical limit. So the path integral on the left-hand side, so that one, the gravitational one, will basically, you can calculate it by focusing only on the saddle points. So you will effectively only get the contribution from the saddle points. So the left-hand side of the path integral will be basically e to the on-shell action, because the saddle point of the path integral is the point where the equations of motion are satisfied. So you get a contribution from the saddle point, contribution from the on-shell action. This form, is it clear? This is basically the saddle point approximation. And so you know that this is dual to the CFT on the boundary, and you can rewrite that source path integral source coefficient function as e to the generating functional. Okay, I'm ignoring here the minuses or i's because I don't want to fix any concrete signature. So you can imagine here, for example. And okay, so this is because we have a semi-classical limit, and this means that what we will be basically doing is to take the on-shell action, where you plug in the solution that reduces in the boundary to some particular boundary value, and this is equal. And this is equal to the generating function now in the CFT. Okay, is this clear? I mean, this is one of the most technical points, one of the most difficult technical points, but so this is basically the key aspect of doing things in semi-classical way. So what to do in practice? So what to do? So in practice. So you have to first solve the equations of motion for this theory. So I will now ignore this part because we will be interested in the correlators of scalars. So this will not be relevant for us. So I will not focus now on the Einstein equations. So in practice, what you are doing is you first have to solve the equations of motion. So the equations of motion is just the Klein-Jordan equation in some background G. With some boundary conditions. So these boundary conditions is that you want your phi to reduce. So once you go, for example, if you use this r coordinate or c coordinates in AdS, you want So once you reach the boundary of your AdS, you want this to behave in some particle way. You will necessarily have some diverging factor, and then you will have the boundary. So there is some boundary condition that require which basically states that you want your field to reduce to this boundary value. And this is the first condition. And the second condition, because of course we need two conditions, the second condition is the regularity bound. So generally, it can be proved that in AdS spacetime, these are well-posed boundary conditions that will always lead you to a unique solution. So you solve the equations of motion and find the suitable phi. Second, you insert it into the onshore action. So you insert it into the onshore action. And use the AdS CFT. So this is the claim of AdS CFT. So this you claim is the generating function for your CFT. And once you have the generating function out, you can calculate anything in CFT. Which means that now you can, for example, a useful quantitative calculators, for example, correlate of this form. And the claim is that this is the source, meaning that in your path integrals, it's you have something of this form, the x, and this means that if you do variations of this object with respect to the sources, you will get correlators of operators. So this is a standard thing in quantum field theory. So this you can basically get as taking variations of this with respect to the sources x and y, and that's it. And you will get this quantity or any other quantity. Once you have this object, you can calculate anything in theory. So this is how you work in AdS CFT. And so why is this useful? So for example, in this particular case, we have no idea what is the Lagrangian of the conformal field theory that is doable. We just know that it should be well defined, but we have no idea how to write it. We don't know what the Hamiltonian or Lagrangian is. The only way how we can throw the boundary in holographic CFT dual to this object is by this procedure. So we solve the bound and calculate the generating functional, and now we can calculate any quantity that we want, and this way we can throw the CFT. So this is the way how you can examine CFT by using bound calculations. Okay, so this is how these things are done. So this is a basic theory. So this leads you to a dictionary. So this gives you some kind of dictionary where operators on the boundary, for example, operators of this type, are dual to fields in the bulk via this procedure. And you will find that the scaling dimension, which is the quantum number for conformal field theories, corresponds to the mass by this concrete ratio. So for example, for our scalar field, it's delta like this. This you can even get this in very generally by studying symmetries in the bulk or on the boundary, and study Casimirs or representation theory, and you will get that this is the way how these two things are related. And you also get with the stress tensor that necessarily has to exist in all CFTs is dual to a metric perturbation in the bulk. By metric perturbation, I mean that you usually fix your G to be some background plus some small perturbation. By the way, this corresponds to gravitons in the bulk, and yeah. And finally, or almost finally, and then I will go into the second part of the talk. It's important. There is an important claim in AdS CFT that states in CFT corresponds to geometries in the bulk. So if you want to study things in vacuum, you basically fix this background metric to be pure AdS. So if you want to study thermal states, so if you want to study, for example, this correlator that we put into some thermal data, so this is dual to AdS black hole. This is one of the most cool statements that Witten discovered in a way. And it is basically based on the research of Hawking and Page. It's actually a very nice claim because you can the fact that you study a thermal state can be phrased in a geometrical way, that you study CFTs in space-time where the time is compactified, it's rotated and compactified to a thermal circle, and then you can ask what are all possible geometries in the bulk that will give you this type of solution, and you will find that there exists only basically 3 possible settle points, and for us the only one is relevant, which is the AdS black hole. So this is an awesome statement that has been used in the past 25 years very often, and is very cool because, for example, you can assume that your CFT is some conformal system that describes some models of quark-gluon plasma, and you can actually calculate hydrodynamical properties like shear viscosity or speed of sound in that plasma by studying propagation of gravitons in the neighborhood of the black hole in the bulk. And this is a very awesome thing that was actually done and had a very, very nice, well, yeah, it's a very nice thing. Anyway, okay, so coming back to this. Now, what we will be doing is we will take this theory and we will aim is to take this minimally coupled scalar and study 2-point function, where for simplicity I set the coordinates x, y, and z, vector 0, and only focus on time. I will put tau, this is the Euclidean time. And we will study this 2-point function, but in a thermal state, where this is the inverse temperature. And we will study this 2-point function in a thermal state for this model. So this is what we want to do. So why do we want to do this? So this is basically the simplest probe into the thermal physics of strongly coupled systems that you can possibly think of. So it has a lot of good reasons to study this. For example, for stress tensors, it's like all those things that I was talking about, and the properties of the strong coupled system and so on. So, but for us, this is the thing we want to study. So, if I now look at what we have to do in order to calculate these things. So, first of all, we are in a thermal state, so we will be calculating things in a black hole background. And what we have to do is basically this first step. This is the most non-trivial step, is to solve this equation. So our aim and the most important thing is to solve. That will be our task for the rest of the lecture. Is to solve equation of this type. So this is the central problem that we have. So this was the first part of solving. If you have any questions, ask.
Yeah, I'm thinking about, you didn't really say what anything about the operator or except that it's dual to
Exactly
the scalar field. So what can one say more?
So at this point, we cannot really say anything. We just know that there is an operator which is dual to this object. So we know there is an operator called as dual to this. Since this is our Valach Lagrangian, so actually in the dual CFT, we don't expect to have any other operators than those constructed of O and those constructed on the metric perturbations H, because from here we'll get some metric perturbations, which will lead to stress tensors. So we will have the stress tensor and the scalar operator, and we expect that the operator content will be only constructed of the composites of these two things. And there will be nothing else. I will tell, that will be in the third part of the talk where I will tell you very concretely what is the operator content. And that's actually the most recent information and most recent knowledge that we gained that allows us to actually finish this whole story of like singularities. So
Usually it's claimed that it's simply traced properly, but you haven't talked about color and large N and so on.
sorry?
So usually it's claimed that the operators in this correspondence, it's single trace operators.
Oh I will tell you all about single trace and double traces in the third part of the talk. Yeah, so that will be actually of central interest to us. But yeah, let's postpone the discussion of that. So, but now now we basically don't know about CFT. Now we just want to solve this equation. And this is the second one. So first problem is that okay, so this is impossible to do. If you plug in the black hole metric, which is slightly more specific, I raised it. This is the black hole metric that we are using. So even if I will now use the recrotated time to make things simpler for me. This is the thing this is the metric that we have where f is f(1) minus r plus the 4 over r, where r plus is the radius of the black hole, or the outer radius of the black hole. So this is so in AdS you have three types of black holes. This is the simpler one. This is the simplest one. This is the planar black hole. So this is the simplest possible situation you can. If you want to have a black hole, it's the simplest black hole you can have. And even with this setup, if you plug this in, calculate the Valach operator, you will find out partial differential equations that are impossible to solve. So you cannot solve it analytically. So
that's different.
Sorry?
Impossible to solve analytically.
Yeah, impossible to solve analytically. Yeah. Yes. So what do you do? So what are the approaches to this problem? So this is a problem in magnetic study. And so first of all, some people use numerics. I don't like numerics. So I don't. The problem is that you can get some plots and some nice things, but you cannot really get any deep physical insight about things. You can get some insight, but not everything. I don't like it, so I want something better. So what is the other most option is that you specify some kinematical regime. So typical thing is to do, you will recrotate this equation, you Fourier transform this equation, and then go into specific kinematical regime like hydro regime. So you take energy and momentum to very low, to very small, compared to other scales in your system, like AdS scale, and this will allow you. This will make your equation to be much simpler. Many people will just drop out, and you will be actually able to get a solvable equation. So this is how some quantities were calculated for hydrogen. But this is also something I don't really want, because okay, you can learn something about the low energy physics, but yeah, that's now you can also what we were doing is one of the newer approaches is to specify the so-called light cone regime, where your two operators are almost light-like separated. This is hard to interpret what this physically means, but the point is that many universal properties emerge and become manifest in this regime, and it's also very interesting to study this. But again, it's not it solves it only in part of the regime. And so on. You can assume other regimes like that. Or you can do some kind of perturbation, like do some direct momentum space perturbation or calculate Witten diagrams.
The regimes are also kind of perturbation.
Yes. All of these things will be perturbations. So yeah. But this is a hard thing to do, and yeah, it's also but you can do it. Another thing, I mean, there are also lots of other experimental approaches, like you can use some instanton counting and actually relate this Valach problem to Liouville CFT, and then relate the Liouville CFT to some supersymmetric four-dimensional problem, and you can actually get this four or quadruplet duality to actually count instantons, then relate them to Liouville theory, and then Liouville theory to this type of Hohen type equation, and then this equation to the CFT, which is also cool, but actually doesn't value too much. I mean, you can do it, but anyway. But what is another approach is to restrict your attention to so-called geodesic limit, where you will solve this problem but just for very massive problems. So you require your mass to be sufficiently large, or respectively your delta to be sufficiently large compared to 1, so that your field equation, your field will basically localize around the geodesic involved. So this is a free field. So it's basically using WKB, and you will basically localize onto the path that minimizes your proper length.
Is it like a iconal approximation?
Exactly, it's exactly the iconal approximation. Yes. And so this is something that I will talk about now. So the drawback of this approach is that, okay, so this is only valid for deltas being sufficiently large. Of course, they have to be large, but not that large that they will back react with the geometry. So this might seem like a restricted condition, but it's actually very natural. It's our black hole is anyway relatively large, and we'll just assume classical particles that propagate through the space-time. Okay, so very good. So in this regime, so this is exactly the iconal approximation, or it's almost the same thing as WKB, which is almost the same thing as settle point. Well, these things are all in philosophy the same things. So what can be found, I will not can be shown that in this limit, basically for these reasons that it is WKB, that your G, let me call this object that we want to calculate, let me call it G of tau. This is the center correlate on the boundary of calculate. So the G actually becomes sum over saddles e to the minus delta times the proper length. So by these saddles, I mean all possible geodesics that connect the 2 points. Usually you have only one geodesic, or in either situation you have one geodesic between the 2 points. And this means that, for example, in the Euclidean case, your space-time looks like this, where your tau, where I ignored the x, y, and z, your tau is a coordinate that goes around the circle. It has a circumference beta. This circle, it's called a thermal circle. So yeah, so here beta over 2. This is the boundary, the conformal boundary of space-time. And what you are asking here, if you want to calculate the G of tau, is that so you start with one operator here at 0, and the second operator somewhere in here at tau. So here's one insertion, here's the second insertion of all operator, right? And you calculate the geodesic between these 2 points. And that every such geodesic, usually it's only one geodesic, will be one saddle. And you calculate the geodesic length, the proper length between these 2 points, and that's this L. Okay, and you will find out actually in the Euclidean case, so once you are using this Euclidean coordinates or Euclidean signature to describe the plane black hole, so the geodesics look like this. So you have, for 0 energy, you will get just a straight line that connects you from 0 to beta over 2. So this is a straight line. So this is for energy being 0. Now, once you increase the energy, this is how your geodesics will look like until you reach almost coincident points. So this point is for energy in both infinity. So these are the geodesics for the Euclidean section. And once you reach this point, you go symmetrically like this. This is for yeah. So it's symmetric in this. So this symmetry is due to the fact that we're in an eternal circle, and this means that. So I will now let me now draw you the complex plane for tau. So what the description tells you is that okay, so this is the real part of tau, this is the imaginary part of tau, right? So here we see that all this description basically happens on this line, and we see that because of this beta symmetry because you have just a eternal circle, which is a periodicity. The only reasonable place to study these things is from minus beta to beta. So this picture corresponds to studying what happens for these taus. Is this clear?
Why not beta over 2?
Yeah, so beta over 2 is here. Yeah, so here you get the yes, I mean you can study it even after beta over 2. You will just get the symmetric results as here. But the point is that once you reach this point, I mean, yeah, there is also symmetry between around this point. But what I want to say is that we will restrict our attention to beta because then there is no meaning to study things beyond beta.
But why go to minus beta then? Why do you want to cover it twice?
Okay, let's not cover it twice. Let's cover it all at once. That's a good point.
So then you have the infinities of your own.
Yes. Okay. So this corresponds to this picture, and this is a very boring picture actually, because in Euclidean coordinates, once you take this to Euclidean, which I already did here, you basically get no horizon, or you will never be able to reach the horizons. It's kind of boring. So what is interesting is to really consider the physical Lorentzian.
Yeah. Right. So where is the black hole? You drew the space. You drew the geodesics. Where is the black hole?
So if you would, okay, so this is the like the projection.
Mm-hmm.
So if you would, so how if I would write it in 3D.
So the table is what? R tau plane.
Sorry.
The table is the R tau plane.
Yes. Yeah. So the R is when you. Oh, this should be the here is where R goes to infinity here.
Mm-hmm.
And this point should be R is equal to 1, actually, the horizon.
Okay, so
You never reach.
So the black hole is there.
Yeah, but this is the horizon.
That is the black. So you're using coordinates where
Yeah, I'm using coordinates, but I don't see the black hole. I mean, I don't see inside anymore. So if I would draw this or inflate this, so the point is that yeah, so this is the R coordinate, and it basically caps off before this is the horizon.
So what is the energy equal to 0 geodesic doing?
That's a good question. So we should go like this.
Mm-hmm.
And go close to the horizon and then go back. That's what I think it does. Let's let's see how it works.
Okay, so we're looking at this picture from above, so we'll see something that goes like this.
Exactly. Yes. So in the Euclidean picture, you cannot really probe beyond the horizon. This is because of the coordinates that we are using. So we are yes. But okay, but this will be even more clear in the Lorentzian case because there I can get easily back to the. So in the Lorentzian case, how these things look like is that okay. So the Penrose diagram for this planar black hole looks like this in AdS. So you have a bending on singularity. So this is the maximally extended space-time. You get 4 wedges. So this will be the most conceptually difficult part. So this is the Lorentzian case. Now here this batch corresponds to the universe outside of the black hole, outside of the horizon. This is the horizon here. This is the interior of the black hole. So in our Euclidean case, what we did was we just took this Lorentzian batch here and changed the coordinates such that you never even encounter any problem at the horizon. So we don't see anything beyond the horizon because so we just reparameterize this batch.
So tau is now up.
Yes. So tau is now or now it's d because it's the Lorentzian time. It's now up.
Yeah.
Okay, and this is a bit more complicated because so you have these 4 wedges. So I maximally extended the space-time. So now here is our standard universe. Here is inside of the black hole. This wiggly line is the black hole singularity, and then this is maximally extended to have a parallel universe in the white hole. This is the standard thing that is done in when you maximally extend space-times. And it's actually very useful because so the only conceptual problem is that okay, so now time here, Lorentzian time flows this way, and here it flows this way, and here it flows this way. So you have to be careful about the error of time.
So that's why you have the minus beta?
Yes, exactly. That's why I wanted to keep here minus beta because so that we'll cover like the extended problems. And now, okay. So now, so let's say here is the 0 t. So this is the t is 0 here. Now, how the geophysics look in this? So furthermore, to give coordinates in this whole extended picture of the Penrose diagram. So you can either use Kruskal coordinates, which will completely cover you this space-time, and it's the best thing to do. But I will not do that because what physicists usually do is that they say like, okay, yeah, I could use the coordinates that cover everything, but I will use the Schwarzschild coordinates and then complexify them, and so that in every wedge I can use them, but in every wedge I will just get some complex shift. So in this, once I will reach the horizon, I will still be using the same type of coordinates, but I will now get plus. Yes.
Usually in the Penrose diagram, you have Penrose coordinates, not cross.
Yeah.
You have to compare them in such a way that the infinities becomes finite with the. There are actually many choices, but for example, your tangent. So actually, that graph is with the Penrose.
Okay, yeah, coordinates. That's true. What I'm just saying is that okay, so the Penrose diagram of this thing is like all the circles. I mean, it's just this. We are in AdS, so there's no other part here. So this is the Penrose diagram, and you have coordinates here. Here you can use the Schwarzschild coordinates here. Here there is a problem on the horizon, but it's just the coordinate singularity. And here you basically get time and r in switch. And you can use this type of coordinates. The problem is that, okay, I mean, of course, what I'm just saying is that if you want to extend this, so this should be banded. If you want to extend this, you would get just some complex numbers. And the Kruskal coordinates is just if you really want to have a real coordinates to describe these things. Okay, that's probably I shouldn't mention Kruskal coordinates at all. Yeah, I mean you can just.
It was just actually.
Yeah, I mean there is no problem with coordinates. Okay. There is no problem with coordinates.
The arrows of t, do you really mean that they both go to the right side?
Yeah.
Yeah, they increase in this direction.
Both.
Oh, sorry, no, yeah, sorry, yeah, no. Of course, sorry, yeah, you're right, thank you.
Good.
And so here you get complex shifts. So this will be the coordinate we'll be using. It is minus beta over 4, minus I beta over 4. And if you reach this wedge here has plus I beta over 4. So in each of these wedges we can use the Schwarzschild coordinates, but here we will get some fixed imaginary part. So these are the coordinates we will use in this context. And okay, and what we will be studying are so-called two-sided geophysics. Yeah, I don't have other colors. Okay, maybe there is.
Yeah, there are.
Oh, there are really. Oh, good, very good. Go into the green one. So Okay, so what we will be studying is that we will start somewhere here on the boundary with some time.
Oh, actually, I think the green one cannot be seen on the video.
Okay. So let's maybe use this one. And we will be for symmetry reasons, we can always study so-called symmetry geodesics, which basically start and end in the same point here. But note that this doesn't mean that the boundary time becomes zero because of the different flow of time. So here you will gain like delta t over 2 or t over 2. Here is another t over 2, and altogether the time difference will be t. Okay, so this is something that should correspond to this tau. So the time difference between the 2 points. And we will have one operator inserted on one boundary and the other operator inserted in the other boundary. So this might seem super weird, but the point is that this will really studying this geodesics between these 2 points. It will be space-like geodesics, so not even corresponding to real particles. But the claim is that studying this type of geodesics, we will be simply examining really the thermal correlator for just this time. This is because we got this shift once we reach from this wedge to this wedge, we get this time shift. So this really corresponds to just probing standard thermal correlator just at this location. So this might look very non-trivial. This is what I think it was Malvasena who came up with this interpretation that you can study this 2-boundary version of AdS CFT, and it basically corresponds to the 1-boundary version if you trace over all the contributions from here. So what we are doing is instead of working with thermal states, we work with thermal flow double states. So it's but I don't want to go into too much details. The summary is that this type of setup really calculates to you the thermal correlation that we want. Okay, and we will be studying the space-like geodesics here. So if we will study geodesics just inside of here, like geodesics that will connect points on the same boundary, then what we will be effectively doing is just the recrotation of this story. Okay, so let me go again to the complex tau plane. So here we have minus beta, beta. So this was the Euclidean story. And if we would just be here, inside here, and study things inside of this batch, it's just a Lorentzian version of that. So what we are doing is just derotation, it's just studying it here. Right? But if we would study system to go from here to here and like go past the horizon and end up in singularities, this means that we would be studying objects here at beta over 4. This is beta over 4 or up to minus, because there is a shift I beta over 4 for the Lorentzian time. But what we are interested in is to study space-like geodesics that connect 2 points on these 2 boundaries, and this corresponds to studying objects in Lorentzian time here with the constant time shift beta over 1. Okay, so this was the maximally most difficult conceptual part, but the point is that this geometrical interpretation of geodesics between these 2 points corresponds to studying the correlator on this line. Okay, is it clear? This is maybe the summary is we will be studying geodesics between these 2 points, and this will give us this correlator. Okay, I mean this is it's just conceptually very there is plenty of places where there is potential misunderstanding. Now the point is that that if you study geodesics, for example, if you would start at 0 and study geodesics of this type, the 0 energy geodesic is this one. This is easy to 0. Note that this geodesic will give you no time shift in Lorentzian time, and it will just give you this constant time shift. So it corresponds to this point here. And it exactly corresponds to this geodesic here, which again gave you beta over 2 in Euclidean time, and it's again geodesic of this type. And it's basically the same thing, because here, as you asked, we just touched the horizon and then came back, which is basically what we will do here. And in this picture, this is basically we just do the same thing, we just go forward. So everything is consistent in this story. Okay, but no. Okay. Now the point is that the generic geodesic between points looks like this. That it goes like this. Its baseline looks like this. This is the generic geodesic. Okay. So yeah, and for example, this will correspond to some point here, right? Because we will have some non-zero boundary time difference, which is here. Okay, it's everything makes sense. It's just you should probably think about it for a very long time. Okay. So now these are the geodesics. And now to come back into the surface of the Earth, let's maybe do some practical calculations so that you can really see these things for your own eyes. Okay, so
Does all the geodesics have two nodes, so to speak?
two nodes.
So to speak. Yeah, I mean, yeah, that it crosses the equal zero geodesic.
I think yes, I think so. Yes. Yeah. Yes, I think so. Yes. Yeah. That's a good question. Yeah, I mean all two-sidedness. So okay. Okay. So explicitly, this is something that might be more easy to work with, is that we will really now calculate those geodesics. So start with union points. And for simplicity, set x vector, which is x, y, and z, to 0, and also set the radius to 1. Okay, so now we still have this metric here. Now what we do is let's just calculate the geodesics. So the thing that you can do is to just calculate to take the geodesic equation and solve it, which is a very bad thing to do because it will take a long time. Instead of that, we can use a symmetry problem. So we have a Killing vector for the time translations, which means we have conserved energy. So this means that we will have conserved energy, which you will find in this form. Tau dot, where this dot is the derivative with respect to the affine internal limit. Okay, so let me call this equation T. Now, the second thing is we want the geodesic to be space-like, meaning that the forward velocity has to have a unit norm. So we are at minus plus signature, so we want the norm to be 1 for space-like things. Or in other words, you start with our metric that we have. So we can formally divide by ds squared. So we divide by ds squared, and you will find that 1 is r squared f tau dot squared plus 1 over r squared f r dot squared. Okay.
So S is dot.
Yes, S is dot. Yeah, S we will fit as in a fine format. And now, okay, so now we can just reshuffle this and r minus r all to the 4 times squared tau dot squared is r dot squared. And now we recognize here the definition of the energy here. So you can together write that r dot squared is r squared f r minus e squared, and this will be our second equation b. These two equations are enough to determine the geodesics. This one and this one. Okay, so it's very simple calculation, and
yeah, so it's you said you're working in Lorentzian, that's why we can talk about space-like, but then you're using the Euclidean metric.
yeah, so the logic is this. So first of all, first I will calculate things for this picture. Okay, I will calculate things for this picture, and then I will tell you how the results can be directly translated into that picture. So I will start by just calculating everything in Euclidean, and because it's simpler, and then there's a claim that you can just do analog of Greek rotation and get the results for that calculation.
Yeah, but it's hard to see what you mean with space-like when you're in Euclidean. So you have to somehow.
Yes, that's true. That's true. That's true. That's true. Yeah, that's true.
But I guess you could.
I see what you mean.
You could just use the Euclidean metric, but
But
the E
let's
will just have a different sign in the definition, I guess.
Yeah. Okay, so let's say we are calculating this type of geometries, but we use for convenience parameterization for Euclidean time. That's even better. That's even better. Sounds better. Yeah, that's a very good point. So yeah, we are calculating that object, but we just we rotate time to make our life simpler. Okay, so okay, and you can interpret this equation as kind of energy balance equation. You can interpret this as kinetic energy and this as potential energy. This we will use in a moment. Okay. Yes.
If I put equals to 0 here, then can I see that kind of trajectory that you drew there?
Yeah, you should be able to see that. Yes. Yeah. So for example, if you yeah.
With the horizon point, the r dot is at r equals to 1, something like that. R plus equals to 1. So that's with the horizon.
Yeah, probably. I mean, it should be. I mean, if you set it to 0 here, you will get the tau dot is 0. So, with some initial quantity, I mean, you should be that. Well, yeah, you should be directly able to see that. It just, I would have to think about it for a moment. But yeah, it should follow from. All right. Okay. So what you can do now is to take this A equation and rewrite the derivative of tau with respect to S as derivative of tau according to the derivative of R. This will be a useful thing to do. So this is d tau over dr times r dot. Okay, I mean, afterwards, it's not why I'm doing this, but the point is that the calculation of the, I mean, solving this system will be easier in R variable, and it's the most optimal thing to do now. And from here, okay, 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 yeah. So, okay. So plugging this new thing in here, I will get that that E is R squared R dot F D tau over dr, right? And now from here I can solve for tau to get that tau is some Euclidean path that I have. E dr over R squared F R dot. And now I want to like this R dot here. So we'll use the second equation to get R dot from here. So from here we know that R dot is square root of R squared F minus E squared, right? So I can use it here, and you will get that this is integral over the bar R squared F R squared F minus R squared, like this. Okay, now what is the path? So what we want to do there is that we want to go with R to infinity, or we want to start at infinity, because the asymptotic boundaries are at infinity. We will go after the turning, at some turning point, the closest point to the actual singularity. So this is, yeah, so it's basically this. Or well, it's actually not. It's not even that. It's this. Okay. Yeah, this is the distance from the singularity, RT. And then we will get back to infinity at the second asymptotic boundary. Yes. So what is this RT? So the starting point you can find from this energy balance equation, where you treat this as a potential. It's kind of potential, and you want the energy condition so that E squared is exactly equal to R squared F of R. And this will give you that RT is, this is a quadratic equation. You will find that the relevant root is this. Okay, so now we know what the RT is, so we can finally provide the integral. So this is the tau of E being integral 2 times the integral from RT to infinity because of the symmetries of this E d R over R squared F square root of R squared F minus E squared, like this. Okay, and RT is the square root of this object. Okay, and this actually looks super ugly if you plug in what F is, but it's actually solvable analytically. You can do it on like 5 pages or on computer, but you can actually really do it by hand, which yeah, I don't recommend. But anyway, so you will find that this is 1 over 2 times log E squared plus 2 E plus 2 over E 4 plus 4 minus I over 2 times other log E squared plus 2 times E minus 2 over square root of the 4 plus 4. And this is the tau as a function of energy. This is the result of this integral. You can just calculate this integral. Okay. Analogously, you can calculate the geodesic path, which is basically the line element integrated over the same path. So using the same tricks, I will just write in the result of this, or maybe first the integral will look like this. So it will be 2 times. Another problem is that it usually happens that you have to regularize the geodesic length because it diverges. So this is the regularized geodesic length. So I will, instead of infinity, I will write R max and take limit goes to infinity like this. And you will have again the integral of this type from RT to R max from dr over square root of R squared F minus E squared minus, and here I extract the diverging part. Okay, and you can calculate this as well, and the result is simple. It's 1 over 2 times log 16 over E to the 4 plus 4, like this. So this way we have basically calculated the geodesic length. So what you can do is you can invert this relation. It will be very ugly, but you can invert it, and as E as a function of tau, and then like it here, and you will get the proper length. Okay, but as I said, so what we have been doing here is we basically calculate things in sort of Euclidean way, despite actually for the two-sided geodesic. So the procedure how to get back is that if you want to get Lorentzian, so what we do is that we take the old energy and set it to and add an I here. And the claim is that this actually will give you the correct results that you will get from the Lorentzian calculation in the beginning, which seems very trivial, but it's true and it works.
Well, it's the Wick rotation.
Yeah, it is the big rotation, yes.
When you have the relation, so you just.
Okay, so it's not, it doesn't even look non-trivial. Okay. But I mean, I would, yeah, let's say it's fine. And this is what we do. So you basically just change some signs here. And all right. But the one thing that actually is important that will change now is that your energy balance equation, which I noted B and I erased it now, is now in this form. It's R squared F of R plus E2. So remember, this was our B, this was our kinetic energy, and so on. So if you now look at and you want to treat this as kind of potential problem, so this is the potential. So it will go like this. So here it behaves as 1 over R squared because of the form of F. Here it looks like minus R squared, and we are growing it by some energy E squared. This is our energy level that we use. Okay, here it always goes through 1 because it goes through the horizon. And as you can see that for positive energies, positive physical energies that will have positive squares of physical energies, you will go through the horizon. And this exactly corresponds to this picture that we brought here, that you reach the horizon, go through it up to some closest possible distance to the black hole, and then to the black hole singularity, and then come back. So the black hole singularity is located here. The R is 0. This is R. This is B. And we see that this point is the turning point. So everything makes sense. And now, but what you notice is that, like, okay, but this is actually interesting because if I rise my energy and I go higher and higher, I actually asymptotically approach the black hole singularity. So for E goes to infinity, you touch the singularity. Anyway, and this is very interesting. So let me study this type of geodesics here. So to do this, so we will do what I said. So we have these two expressions, and we will just invert one and put it into the other one. So as you can see, I mean, it's impossible to analytically invert this function because it's very ugly. But what you can do is you can expand it. You can expand tau as a function of E, and you will get something like this. You expand it around E is equal to around E goes to infinity. So around E goes to infinity. That's the point we are interested in. So and you get something like this. It's 2I over E and plus some even term plus some terms of all this. Okay, and this you can invert order, and you will it will be a good idea to visit a constant. Let me call this constant tau c, and let's define delta tau, which I'll just put it on the left hand side, and I will define this ratio tau minus tau c. Okay, and I invert energy as a function of this delta tau. Okay, and so this you can do order by order, and so you will find that this is 2I over delta tau minus I over 10 delta tau to the third, and plus higher order term. Okay, so we see that. So first of all, what we see is that once you send E to infinity, your tau gets closer and closer to the tau c. So E goes to infinity means that tau goes to tau c. So tau c is the boundary time that you have to start with to touch the singularity. So the trip is equal to touch the singularity. So if I want to draw it here, so here will be some time tau c for which you go and touch the singularity and then come back. Terrible picture, but is it clear? So this is some finite value tau c,
I'll see.
tau c over 2, or its Lorentzian equivalent. Here it's a bit messy with these different times that I'm using here, but okay. And this is the time for which you go, touch the singularity, and bounce off. Okay, so this is called the bouncing singularity, the bouncing geodesic. This is the bouncing geodesy that bounces over the singularity. And why it's important? It's because where's my shoulder? And why is it's important or interesting? Is because so we can continue this analysis. So this is your E. So we can plug it into the broad length, to the geodesic length, and you will find that geodesic length is 2 times log of delta tau plus terms analytic in delta tau. Okay, and as you go closer and closer to the bouncing singularity, this term just is irrelevant. But now remember what is the prescription up there for the correlate we are interested in. So we find that so this is e to the, well, this is proportional e to the minus delta times the total length, and this will be 1 over tau minus tau c to the power 2 delta, which is a pole. So we find that from this naive form, well, it's not naive, from this geodesic analysis, we find that for the bounding geodesic that goes and touches singularity at 1 point and comes back to the second asymptotic boundary, this corresponds to the pole in the correlator on the in the thermal correlator, and that is located at tau c. And this is called the bouncing singularity, because it corresponds to the bouncing geodesic. So this is bouncing. And it's at tau c is pi over 2 plus I pi over 2. And note that at the beginning I said r plus to 1. R plus actually is beta over or pi over beta. So if I recover the original units, so this is beta over 2 plus I beta over 2. So there is a singularity located at this point. Okay, so let me just so this whole analysis just led to the following picture, that if you look at the complex tau plane for the thermal correlator, so here you have the beta, here you have minus beta, here you have beta over 2, and this means that on this line you will have singularity here and here. This is because you can do the same thing from the front. So beta over 2 and beta. And so your correlate will blow up at this much. And this would be very interesting because it would be measurable in a way in thermal systems, conformal thermal systems, and in other and it will be other interesting things, because this bouncing geodesic is that touches singularity is very specific for the spacetime that has singularities, the black hole singularities. So the properties of this bouncing singularity actually give you information about the black hole singularity. So this was proposed to be the boundary signature of the black hole singularities in AdS CFT. Because from the location of this pole and from the properties from the factors above and from the powers that you have here, you get actually information about the curvature singularity in your spacetime. So so people were super excited that this is the way how we can use CFT to study the black hole singularities. But the problem is that very quickly people realized that there actually exists a theorem which says that there cannot be such singularities. So there actually exists a theorem saying that G tau is regular for any tau for any interval where the real part of tau is between 0 and beta. So there cannot be singularities of this type. So what did we did wrong, or where is the hidden problem? because we really found this type of singularity, this type of geodesics, and they really lead into singularities. The problem is that there are more geodesics that connect those 2 points. There are three geodesics that actually connect those 2 points. 2 of them you don't see, or you neglected them because they are complex. So there actually exists 2 more geodesics. The problem is actually hidden and can be easily seen by the fact that if you take tau as a function of energy and L as a function of energy and expand them around beta over 2, so expand them around this point here, so you'll find that this looks like e to the third, and this looks like e to the fourth. So plugging this here, you will get that this is like time to the 4/3, and you will get 3 branches, 3 complex, 3 branches, one real branch, so one real branch. This is the bouncing geodesic. And we will find 2 complex ones that people thought are not physical, but actually these are the only ones that are physical. Because these 2 complex ones that I cannot even draw there because they have some complex parts and it's not easy to see them, but it was shown that actually these 2, if you do careful analysis of the saddle points, that's why I put sum over the saddles, because you have to sum over all contributions in the saddle point approximation, and this one is always sublinear. And the ones that will, and the true contributions come from the linear combinations of these 2, and combining them, you will get a real physical result that will be real. The imaginary parts will cancel, and this is what gives you real physics. So the point is, people got very sad at that point because they realized that, okay, I mean, this would be such a nice probe to the black hole singularity physics, but for some reason, this bouncing singularity is not physical, or respectively, it's pushed to a non-physical sheet. So you will have to do analytic continuation that is not what we should do, unphysical one, not the one that will give you a real physical result. So it was hidden in a way. People claim that it's hidden in the second sheet or something like this, which I never fully understood, but the point is that you would need to do unphysical analytic continuation to get it. So this was 20 years ago, and people somehow, this was a very popular story at the time, but people somehow lost interest because it was very unclear how to understand these things. Okay, so this is the end of the original story. And now the next and the final part, the new part begins. And that's the last part of my talk, where we gave where we somehow resolved part of these problems and give a better understanding of these things by accident. So it was not, we actually meant to study something completely different. We were studying KMS singularities, and we were getting wrong results that we didn't understand why we were getting wrong results, but we found out that it's actually not wrong results, they are just connected to this. So let me just quickly tell you how the story goes. So let's get back to the original problem of solving the correlator. So we have a correlator. Tau 0. We have this type of correlator, and we want to solve the corresponding Klein-Bordel equation in the Valach, which is a hard problem. Again, you cannot do it analytically. You have to do some kind of perturbation. But what we have some new information that we didn't have before, because in the past 10, 15 years, people were studying the operator content of holographic conformal field theories, and now we actually pretty well understand what operators exist in these holographic series and how do they contribute. So we can use the OP structure of the holographic CFT. So let's use the OPE. So it was found that these 2 conditions that I wrote at the beginning, you want to have large central charge and you want to have large gap. These 2 conditions basically completely restrict the spectrum of all possible operators that you can have in your theory. All of these all will be extremely sublinear in large CP, and there will be only 2 classes of operators that will contribute. So let me just call that. So the identity operator, stress tensor, and then a higher stress tensor, so-called multi-stress tensors. But let me know them increase and then the third, and significantly many of them. These are operators that you can composite of two stress tensors. So these are operators of this type, for example, or you can put some derivatives here, or you can contract some indices. So actually, you get infinitely many of them in each of these brackets. But we have good control over them. We know exactly what is their spin and what is their conformal weight. So we understand all of them. We understand how they contribute. And so this is one sector of the theory. This is called the stress tensor sector. Stress tensor sector of the theory. And besides this, this is universal and exists in all CFTs. We would not be able to get rid of it in any way. And then, because we are working with the scalar field, the only other sector of the theory is so-called double trace scalars, which we usually write as this OO and L, and these are operators that that looks like this. So it's O, and then you have some the Lambertian operators acting on this, and then you have some operators with three indices, and L of them acting on the second operator. So these are the only primaries, quasi-primaries that you have in your theory. Besides this, you have their descendants. Everything else is suppressed. Everything else. So the triple operators, the single O operator, the triple O operator, any other operators you can possibly imagine, even the combination of P and O, all of these are suppressed if you do careful around large CP counting. So we have complete control over the operator model. And that's very good because now besides the fact that we have the complete control over this, we have CFT methods that gives us the concrete kinematical factors that contribute that correspond to any operators. So we can either study so-called thermal conformal blocks, or we can study, we can see the thermal correlators as some heavy light operators and use conformal block decomposition. So we can use these very technical tools that we have, and we can write down the correlator G tau as a sum of these two sectors, as we call it GP tau and GOO of tau. And we can simply write it as this. Significant sums over tau over beta n plus 0 to infinity dk 12 over beta to 2k plus 2 delta. This is the most technically difficult part, but I completely skip it. This is the result where I already set x 0, and I also sum over all spins, because unfortunately you even have like different spins according to how many contractions you do between these operators. They have different spins, so it's technically very complicated. But at the end, you will get a very simple result. So this corresponds to the stress tensor sector, and this is the double trace. Okay, so we know that this is the correlate, and these are the constants. These are only constants. There is significantly many of them, but there are constants. So we know what the structure of this correlator has to be just from the CFT analysis itself, and we can determine it up to constants. Okay, but this actually didn't bias anything, because we know that conformal symmetry is usually that strong that we can restrict everything up to constants. So this didn't help too much, but at least we know how these things organize in blocks. And in 2019, there were two clever people that found out that, okay, so what if we construct a Valach ansatz that will solve us this Klein-Gordon equation in the black hole background from the knowledge of the structure of these blocks? So they used the result that they know that they should get. They know that they should get the sum of these blocks in a way, and they constructed a very clever ansatz that allows us to solve perturbatively, but very nicely, the Klein-Gordon equation. So they first, by studying two-dimensional case and like AdS3 and doing some very clever tricks, they discovered that, okay, so we first have to use some very unintuitive coordinates. and rho is r to the x, like this. And in these coordinates, we can formulate huge polynomial answers. So that will look like some vector that we will get in your AdS that we know analytically, and then 1 plus, and you have just sums over n, j, k of some numbers, n, j, k, and then just a huge polynomial in rho, w, and r. And they found out that imposing the regularity in the Valach, these sums, so this is an infinite sum, this is the main sum that we do perturbation through. So we do perturbation in 1 over r, which means that we solve the equation by looking around the boundary point. So it's called a near boundary expansion. And they found out that these two sums have always finitely many terms. So they basically propose this huge polynomial. So you just take this polynomial and plug it into the Klein-Gordon equation up to order that you can calculate. So you fix some order here, plug it into your equation, you will have a huge polynomial like there, compare the coefficients, and you extract these numbers. And this answer is constructed from the knowledge of these blocks, and it's built in the way that each order in n is mapped to concrete order in n on this side. So these coefficients are directly combination that will give you OBE coefficients here. So it's a very clever way how you can solve the Valach problem and directly get the OBE data on the boundary. Okay, and yeah. So the slight problem is that you can get all the stress tensor sector, but you cannot fully determine these coefficients. So, but fortunately, we'll just ignore this. We'll not focus on the main one. But the point is, it will be enough for everything because I mean, we expected this because it's just a near boundary expansion, so you cannot get full information about the structure close to the black hole, which is in the center of the spacetime.
And what they wanted to know. They wanted to know about the black hole.
Yeah, but as I was showing you, this is enough, and it's actually very lucky to forget about this because, yeah, just a moment.
We were talking about that only that, not about the TP sector.
No, but
Why are you saying we cannot?
No, but this part also knows about the structure of the black hole. It's just that this answer is able to determine. This one needs more things.
So it's the phi couples to the O, which is the thing that appears there. You're trying to solve the equation for phi, and you're not able to solve for the things that contain the O operator that phi couples to, but only to the
Exactly.
one.
Exactly. But yeah, but so one of the things why we don't need to care is that at the end we will want to compare it with the OP with the geodesic analysis. And this is suppressed by these delta powers because this is number less than 1. And setting delta to infinity, this will be subleading compared to these logs. So it's for many reasons this is kind of irrelevant. Okay, but now the point is that like okay, so we can calculate these coefficients. So what we did was that we calculated them. We had several of them up to several high orders. Then we calculated more and more. Then we calculated even more. And then we had when we plugged the answers, because the answer grows very quickly, it goes like n to the power of 5 or something, the complexity of the answers. And so we calculated the coefficients, and many of them. And at some point we had like answers that had 15 million terms, and that was not enough for our computer to calculate it anymore. So we started to use the supercomputer cluster that we had, and we calculated more and more and more. And then we calculated the coefficients up to n is equal to 50.
I thought you didn't like computers.
Yes, but it's analytic as well, because we will get the coefficients analytically. So there are no approximations there.
So, what were you calculating the answers or the OPs?
Sorry?
What were you calculating the answers or the OPs?
So we calculated the answers, and we forget these coefficients from the answers. And but the point is that then you can take a limit. That's a good point. I forgot to mention this. That you can directly get these coefficients if you take large R limit of this result here, this one, so of phi, when you translate back to the original coordinates, so back in r, tau, x, and large r limit of this with some factor r zero delta, it doesn't really matter. The point is that this part will be mapped to this free factor, and this part will be directly mapped into this object, while this lambda, the OBE coefficient, will be just combination of these coefficients. So basically, getting this, we can relatively trivially get OBE coefficients. And so we calculated things out n is equal to 50, which takes for a particle delta, setting particle delta, it takes 10 days for a computer to calculate that the order of 50s. And you may ask, okay, I mean, this is a terrible waste of computational power, because I mean, why would you need it? It's really a terrible waste of computational power, but luckily we found something very interesting. So we found that these coefficients lambda n, they were just numbers. But analyzing them, we find that when n goes when n goes to infinity, it pretty quickly converges into a particle asymptotic form, which looks like this: for n e to the I phi. So some particle form of this type, where we see we cannot determine fully, but we know the whole structure of this, and basically we know it very much. And this is the asymptotic form.
But this is just a guess.
It is just a guess, but thanks to the fact that we have data of more than 50, I mean, we have precision that is almost like we are sure of this up to like almost infinitely sure that it's true. I mean, it converges to this extremely well. So for particle deltas, I mean, you get I mean, the convergence will look like for any setup, for any deltas, for anything, it will just go like this. And it's exactly that, like for almost anything.
I mean, there are some theorems that for any finite sequence of numbers, there's an infinitely many formulas.
Yeah, exactly. So that was the problem why we need so many of them.
But I guess you can always call it a conjecture.
Yeah. Yes, but I mean, it's I mean, really the data is really reliable. It's yeah, but you can never be sure. I mean, but I mean, it is this. On the level of like physical precision, it's not a matter of the theory, but on the level of precision that you can get, I mean, it really is. So we are sure. And okay, yeah, but yeah. I mean, we were sure that even if we had, even when we had the 10 data points, the more that we had, it went even closer and closer. So, okay, yeah. So, and once we have this, what we can do, we can try to do a very simple thing. We can sum the OPE. So we know how the OPE looks, and we know this is the OPE, and we can just sum this stress as a part of the OPE. So this is almost the end. Because, so now this is the OBE, 0 to infinity, lambda n, tau over beta to the 4n. And now I will, this is the spectrum I wonder I cannot do, but at the end I will show I can do. I will approximate it by an integral. So this is 1 over tau delta, 0 to infinity, lambda n, tau over beta to the 4n, dn. Okay, and now I can plug in the large n result. So I will just plug in this formula here, and I will get that this is c of delta over tau to delta integral 0 to infinity and to delta minus 3 over 1 over square root of 2 or n e to the I n tau over beta to the n dn. Okay, and you can actually do this integral. It's doable. So this integral exactly this value, which is gamma function to delta minus 2 over tau to delta, and now minus 1 over log of tau to the 4th power over beta to the square root of 2 4th power e to the I to the Okay, so this you can do. Now, okay, you may okay. Oh, false part. Now, the only end of basically this talk is that so if you look at the result, this result, it blows up at some point. It blows up whenever the argument of the logarithm is 1, because then the log is 0 and the 1 over 0. Right? So it blows up at tau is e power square root of 2 e to the I 5 over 4. Okay, but what is this number? Well, this number is exactly beta over 2 plus I beta over 2, which is exactly the tau c, the location of the bouncing singularity. And it's exactly this. And so you may wonder, okay, well, how is this possible? Isn't this just a coincidence? Because I mean, honestly, like these two numbers are very basic. So I mean, it's maybe it's just a coincidence, but no. We did the same analysis in d is equal to 6, d is equal to 8, where the location of tau c from the geodesic analysis is much more complicated. It looks something like this: e to the I pi over d to 2 sine pi over d. In 6 dimensions, it gives you some very stupid number of 0.8, 2 times 0.8, 4, 7, something like that. And we exactly recovered this number. We exactly recovered it in 6 dimensions, 8 dimensions, and everywhere. And not only that, we can also assume subleading corrections to this. So there are corrections in 1 over n in this, and all of these corrections are exactly matched to the subleading correction to the location of the black hole singularity from the geodesic analysis. And even more, we can, if you look at now you will take the limit that would give you the geodesic length, which is the limit of delta goes to infinity of minus 1 over delta of the log of the GP object. You will exactly get cancellation, and assuming this form of one-time coefficients, you get that this is 2 times log tau minus tau c, which is exactly what we got from the geodesic analysis. So in other words, it is GP that has the complete information about the bouncing singularity. And how, I mean, this looked like a miraculous discovery.
And this can have the divergence.
That's the point. This can have a divergence because there is the second operator, which actually, so G is G plus G. So this can have the divergence because this will have the opposite divergence and this will be finite. So, and this is actually a thing that happens very often. That you have some poles here and they are cancelled by analogous poles here. So this is fine with the theorem because it is the partial structure of the toroidal that gives you the bouncing geodesic and not the full one. So everything makes sense. And in this way, it was even lucky that we were not able to determine the double vertices, because there we might miss the fact that it is only this part that gives you the information about the black hole singularity. And in this way, this exactly gives you the boundary description of the bouncing singularities, which are direct signatures of the black hole. So by studying the stress tensor exchange and the multi-stress tensor exchanges, you can learn about the structure of the black hole singularity. So this is the boundary signature of the black hole singularity that we were looking for. And it was a miraculous accident that we found it, even though we were looking for something else. And yeah, so and now, yeah, so maybe just last 3 words is that, so now we have many other options that we can do. Now we can add spin, or we can add charge to the black hole. It still will be solvable, it's just harder. Or we can assume spherical black holes, that's what I'm doing now. Or we can add some corrections like the alpha prime corrections from string theory and see what will happen with these poles if we expect that these bouncing singularities will become finite bounds. And this is called studying the resolution of black hole singularities. So, and now we have CFT tools that we can use. Before we didn't have them. And it's nice CFT tools because it's basically using a huge polynomial that you plug in and come compute it on the computer. So I mean, I think it's pretty nice. Okay, thank you very much. Thank you.
Do we have any questions? So the double trace part of the query, does it correspond to the complex geodesic, the tool you found?
Yeah, that's a very good question. Yeah, yes, it does. Yeah, I mean that's the situation becomes slightly more subtle once you really want to go very deep into this large delta limit. But yes, the double trace part, this part exactly will correspond to one of the two complex geodesics. So you can actually trace this completely. And I don't want to go into too many details because this then becomes very complicated of what exactly happens to this object. Because in a way, this will also give you the second complex geodesic. But there are other things. There is a mathematical. There's things that is called a uniform convergence breakdown that will make some technical mess. But I don't want to go into this. But yes, you can. This is one of the complex geodesics.
And are you able to calculate at least like part of the overall correlate so that you can see that it's finite?
No, unfortunately not. So this is one of the things that's very unhappy in this business. That no one was ever able to calculate, not even a single bar of this. So the most recent discovery was that somebody used some terrible numerics to calculate the first contribution to this object. But with the old supercomputer power that in UK they had, they even estimated roping coefficients like 1.1 plus minus 0.2 or something like that. And this is terrible because and it was provided to set up this game 3 over 2, which is a very special situation where things simplify. So this is unusual anyway, because you would need.
We will know that at least for the code TC should have the same form as the stress energy conservation because they're supposed to cancel this.
That's true. That's true. So in this way, so that was one of the ideas that we could use the fact that we need the cancellation for the theorem whole. So we would be able to somehow match it with this part. The problem is that here is also an infinite sum of terms, so we didn't find any reasonable way how to get anything reasonable. We only know that, yeah, indeed this should cancel it, so we should have an overall sum form such that it cancels, but yeah, it unfortunately is not very useful. But that would be great if somebody would talk about these things. Yeah, thank you. That's very good. Any more questions?
So the fact that these Valach coefficients going to converge to something relatively simple, does this suggest that there's another way to solve the problem? Maybe?
Yes, so that's also a good point. So we try to adapt this ansatz so that it basically uses this fact that these lambdas converge very quickly, and we try to develop some methods that do this, but we cannot successfully. But yeah, this suggests that there might be a much more effective and much more reasonable way to solve this problem.
But you don't know if there's some convergence for those age, for example, in the ansatz. So we combine them to the lambda.
I mean, we have some partial information, like we know which parts of these are actually relevant for these coefficients, but interestingly enough, individually they seem to have a very weird behavior. So you really need to sum all of them to get a behavior that converges nicely this way. So between these coefficients, you will even have coefficients that have stronger divergence with n than 2 delta minus 3, and those with lower one. And it's in some way they have to combine to give this relation, which is very strange summation problem, but we were not able to get anything in this way.
I have another question, which is what's related to what Stan asked you, which is you have the Paris diagram. Okay. So for example, a geodesic node for the result one with energy equals to 0, but others, okay, which connects 2 points the boundary of arrows, right? You drew cursor which, for example, passes through region 3, 2, and 1, right?
Yes.
That are not totally connected. So which means that those geodesics are space-like. Why do you consider them as part of the? Why
Yeah.
are those geodesics allowed?
Yeah, that's a very good
Because
question.
I imagine, for example, that all the geodesics can pass through the origin, but actually, no.
Yeah, so that's a very good point. This is something that I don't know if I completely fully understand it. And for me, it's very non-trivial claim that if you have this Penrose diagram, so indeed what you are studying is studying our basic geodesics that are not causal in any way. I mean, they are space-like. So like if they go like this and then they return, they really go like back in time, back in Lorentzian. So it seems like this shouldn't give you any physically reasonable thing to like why should this correspond to some real quantity in the correlator? But so I don't know if I can give you any good explanation, but there are good references for this. This is the theory of this. It's called the two-sided correlators. So this is it's two-sided correlators. This basically works with the version of AdS CFT where you don't have one assembly boundary but two. And there is a claim. I don't know if I have a good physical understanding of this, but there is a claim that the correlator you calculate using this very strange, unphysical looking scheme will be just the one that you would calculate in your physical wedge for time-like geodesics, but it will be just shifted by this complex time shift. And this seems to me very non-trivial. This has to do something with the theory of thermal doubles, where this is a relation basically between the thermal states that would correspond to the one-sided story and the thermophile double states that are summed over, like you trace over them and you have the original story. But I don't know if I have this is in one of the Malasena's paper at the beginning of the 21st century, but I don't know if I can.
I remember that you said that those geodesics are real, right?
Yes. So you're asking why do we want? Yeah, they are real. I mean, in the sense that they have real values and yeah.
And for example, is there some physical interpretation of that, like crossing the horizon and go back in time?
Yeah, I mean, you can see it like that. That's basically what happens. I mean, you cross the horizon, at some point go back in time and go to the parallel universe and so on. But in all space like particles. So I mean, it's not it's like tachyons or something. I mean, it's just not a physical particle. But the summary is that this unphysically looking setup will actually give you something relevant, so something that is directly happening inside of the Lorentz wedge. So that's
It's a little bit like an instanton. You're looking for an equation solution to the equation of motion, which gives you a stationary point. It doesn't have to be like a solution to the real. It doesn't have to give you a real action or a real solution. Like an instanton, you also have to go to weak rotate and look at the Euclidean equations.
yeah, I think it's something like this. But this is one of the things I want to understand more because yeah.
At some point, people were looking at. I guess they were working with equal force bearing mills and trying to calculate force between quarks by having about again 2 quarks at the boundary and then having a string in the bulk connecting them.
Yes.
And that's sort of similar because the string would hang around along some kind of minimal action curve.
Yeah, I think it's a similar type of calculation. Yes, this.
Yeah, but here you don't imagine that there's a string there.
No, fortunately no. I guess that would make things more.
So, well, I mean, I guess, you shouldn't think of them as geodesics in the physical sense. They're solutions to the equations of motion.
Yeah, yes, yeah. Exactly, that's why I didn't want to give too much physical interpretation to them.
The solution must only be space-like.
Yeah, so that's how it comes out. I guess.
Does it make sense to think of the weak rotation as literally a weak rotation, where we think of it as a continuous process from Euclidean to Lorentzian signature? So, and if that could this triple of geodesics, would that
Maybe, I mean,
can we somehow follow triple of geodesics from one side to another?
maybe yes. I mean, this was also a way I have to think about it at some point, but I don't know if I mean, to me, there seems to be some subtleties that I don't know if I can with clear hard forget about. But maybe, yeah, maybe.
But there are three solutions on both sides of the rotation.
Yes, I mean, in this sense, yes. It just, I mean, if you work so like only in this first wedge, and you rotate this part, and you really then work with this brilliant feature that is just like outside of the horizon region. So here you have only one, like here you have a unique choice between points, but it's also because you are considering. Yeah, so, okay, so in this sense, there is only one, but then if you are considering two-sided ones, you go
Right. Yeah, I'm talking about the two-sided.
Yeah, so in that case, yeah, that should be three on both sides.
Yeah, and similar to WKG, right? You look at trajectories going around.
Exactly.
uh,
And then
two different-
dominant and subdominant.
Okay, any more? By the way, I wanted to say that this summation might seem very, like, well, if this is not approximation, but actually, so this resumming wouldn't be legitimate anywhere, but it is legitimate around the points where the result blows up. This is there's a mathematical theorem. I don't remember the name of the guy, but
It sounds like McLaurin. Related to that.
maybe, yeah. And actually you can even do this at the level of the sums, and you may, because this is called the whole large transcendent, and you don't know what values it really does have, but there's also mathematical properties, and you can actually see this as expansion as an integral plus corrections, and you can see that in large n, which is relevant around the pole, these corrections will be focused very quickly, and you will really, I mean, this is completely legitimate. So I can even write equality if you are only interested in the location around to define things here. Okay, thank you very much.
So, next week, if I don't remember who's gone, maybe you are, but Martina agreed to tell us about what we'll be doing. Okay, so, it's a very
Yeah.
Should I stop the recording?
If you want to say, yeah, 20 seconds.